Okay, so today I want to go back to quantum probability setup, the way we defined quantum probability, way we generalized classical probability to quantum probability. And I want to talk about something called few things which are not possible in quantum setup. What we want to call as quantum impossibilities, something called no cloning theorem, and then Heisenberg uncertainty principle. These are the two things I want to talk about. So I will prove two versions of uncertainty principle. This is not, even though it's not part of quantum communication, but this is part of any kind of quantum information theory you have to do. In quantum computation, there is one version of no cloning theorem, which is very easy, which just says that if you have some some state, which is a pure state, then you take a fixed state, something, this going to this, patterns are time. No cloning theorem says that you cannot clone a quantum state, that you cannot copy it. So if you have one copy of quantum state, say chi, you cannot get another copy of, you need this, this is some auxiliary state, this is fixed one. This is for any row, this is for all time. You want to take something like that. So you cannot have a unitary operator which does this job. In quantum computation, you use unitary because it's all unitary gates. That's what they are using. So that's fine. But we will prove as much more general version of this no cloning theorem because we are using completely positive. For us, an operation or evolution of a quantum system is through a completely positive math, and we prove for completely positive math. That's what you want. So I want to recall, first I want to recall the quantum probability setup. So we have been using this is our quantum probability, which we were using in this course. That is, you have a M and C and you have a rho. So this is a quantum probability space where this is our, you have a state on this. This is a operator, positive operator, rho greater than or equal to 0, such that raise rho equals 1. But if you recall, our general setup for a quantum probability is you have an algebra contained in MHC, general setup for our quantum probability space is A contained in M and C. You can have any C star algebra, finite algebra, if it is infinite dimensional in some Hilbert space. That's also possible. In finite dimensional, it is just an algebra. You don't need to take closure or something. It's finite dimensional, it's automatic close. And you have a phi from A to C, which is a state. This is the generalization of probability measure. Okay? This is the generalization of probability space. Whatever the measure space. You have functions. So if you have listened to the first lecture, so any probability space omega script f p. Okay? You can identify with functions. This is if it is finite. If it is infinite, you have to take appropriate phenomenon algebra or something, or sister algebra. So you can work with anything depending upon your framework. Okay? So then you have C of omega is just, if it is finite, just functions. It is just m tuple. Then C of omega, and you have, using this P, you can get a state on this. Okay? You have any state, any linear function on this are given by probability measure. That's what, even if it is continuous functions on omega, then that is given by probability measure. They are the linear functions. That's what Rees representation theorem will tell you. Okay. Now this is finite dimension. So C of omega star is also C of omega only, and that gives a measure at each one of them, the function which will give each one of them, and then you can embed this as diagonal algebra if this is of in M and C as diagonal matrices, and there you have the state. Okay, the same P will give you a state there. Okay, so our generalization is you have a algebra containing in M and C. It need not be if it is commutative. So incidentally, I didn't prove if it is commutative, then it is actually given by a C of omega. That is what is a version of Gelfand theorem. But you have seen in sister algebra course the Gelfand-Lemma theorem. That is for any commutative sister algebra looks like this. Okay, and commutative phenomenon algebra will look like L infinity. So those are different. But there is a version for finite version has been proved in the previous course on finite quantum probability course earlier, which video is there. I will add it in the playlist. Okay, so any commutative algebra containing star algebra. This is a star algebra, not the sum algebra. It's a star algebra. And so this any commutative algebra will look like C of omega for some omega finite set. I mean, it's all functions of finite set. Okay? So now we have an algebra contained in MNC and phi is a state on that. So in our case, when A equal to MNC, then the state phi of any A is given by trace of rho A. Okay? For some rho. So that is how we get this. That's why we fix a rho and work with that. Okay? And this is the state. So in general, this is our thing. Okay? So for any, so this is our thing is A phi is a quantum probability. Okay? Quantum probability. So we want to prove, I mean, I'm taking general quantum probability space instead of MNC because I want to prove that if something happens, something is satisfied, then I want to prove it's an abelian. It's a classical case. So I want to include classical. If I take MNC, then that is purely non-commutative. It's a factor. Okay, everything commutes with all elements is only complex. I mean, scalars, constant times identity. So that's the thing which commutes with everything. So I saw there is no way it's a bit. I mean, you cannot have abelian case there. So I want to prove that if something, if you can clone, I want to prove no cloning theorem. So I want to prove a theorem that if in case you can clone, you have a cloning machine, quantum cloning machine, whatever, if it clones the state, then this will become classical. It will become, this will become commutative. So that's what I want to prove. Okay, so that's why I'm taking this. Okay, I'm proving, of course, for finite dimensional case. Okay, so what do you want to? We want to prove that it's not possible to clone. So I will state the theorem later. Before that, I need some lemma. This is something I have proved. I mean, I have asked in the exam, but here I'm just proving it. So CP, everything is. I mean, even though we use for MNC, you have a phi from A. This is contained in some MNC, and this is contained in some MMC, whatever. From two algebra. I mean, we work with concrete. See, in general, an algebra may not be inside MNC, but we consider these are what are called semi-simple case, semi-simple algebra. I mean, in general, algebra can be anything. Okay, there is no reason it's contained in this. Okay? So we are considering a special case. That's subalgebra for MNC. That's what we are considering. Then if you have a phi in that, then you can talk about 1 tensor phi from. I mean, 1 tensor phi from. I mean, you can amplify this Mn tensor A to Mn tensor B. And this map should be positive. That's what completely positive. Okay? So you can use the same definition. Okay? So if we have a phi from A to B, ABR algebra is CP and unital. Yeah. One more thing I want to make a remark. I will make it clear. I have talked about it. I'm just recalling it again. There are two pictures. One is called Schrodinger picture. The other one is called Heisenberg picture, whatever, the covariant version or something. So we already talked about it. If we have some A, algebra A, so we want to, so usually our phi is between, which takes states to states. That's why, if you remember, that's what we consider. Then it is equivalent to, if usually we want to consider phi, an operation, is which takes states on A to states on B. Okay? In the case of MNC, these are all positive operators with stage 1. These are all positive operators with stage 1. So suppose if we have something, so but this again in MNC only. Okay, this A star is also MNC. So when it takes positive operators to positive operators with stage 1 to positive operators on stage 1, then you can extend it because it's finite dimensional. You extend it to the whole thing, and that is equivalent to saying you get a. If this is phi star, then you have a phi from MNC to MNC itself. Okay, in case of MNC. Okay? In general, these are the two things. If you have a phi from A to B, of course, finite dimension, okay, you don't need to worry about other things. But if it is infinite dimension also, you can define phi star. If you have two Banach space, some x to y, then you can define a phi star from y star to x star. You can always define with the same prescription. It will be bounded. Okay? So here it's easy. Here it's clear. You don't need to worry about boundedness. The definition itself will give you a linear function, and that's enough. Okay. So phi from B star to A star. This is the two two version we want. This is what is called Schrodinger picture. If you consider linear functional states, this is what is called Heisenberg picture. This is the version which is easier for us. Okay? So usually the maps are defined as trace preserving. So usually our quantum channel, which is a CP map and which is also trace preserving. So that has to be defined here. Here there is no trace preserving is only for MNC case. In this case, it should take states to states. That is equivalent to saying it is trace preserving there. We have been using a quantum channel is some phi completely positive map defined on MNC to some MMC, which is states trace preserving. Then it will take states here to states here. Okay. Here there is no trace. We are not working with trace. We are having general thing. So we have phi star to phi star with states preserving. I mean, phi star of any state is a state on A star A. Okay. If you have a state, sorry, there is a phi star of any state should be a state. Okay. That is equivalent to saying, if you can check that, phi of 1 is 1 unital. Okay. In MNC, we have already seen, if you have a CP map, if it is trace preserving, then the dual map has to be CP, will be CP, and it will be unital. I mean, in case of MNC, in A equal to MNC, okay, if we have a phi is phi star is trace preserving, is equivalent to saying phi is unital. Phi star is trace preserving means it takes states to states. Okay, that is equivalent, it's unital. In fact, we know the cross operator. If phi is given by phi of x is equal to vi x vi star summation, then phi star x will be given by summation vi star x vi. Okay, we have seen all these things. Okay, so if it is trace preserving, that is equivalent to saying that the if it is, I mean, if it is unital, if it is, I mean, it's trace preserving, it's equivalent to saying that summation vi star vi equal to 1, which is same as saying that this is unital. Okay, so here the same thing you can look at here. I mean, this is an easy exercise. So I haven't said what is the definition. Let me just. If we have a phi from A to B, okay. I mean, I had written A star to B star, I interchange it, doesn't matter. Okay. Then phi star corresponding to this phi star from B star to A star, you can define such that phi star acting on a rho B star, rho B, B star is rho B. Okay. Rho B has to act, phi star of rho B has to, I mean, this has to land here. Okay. This has to act on A. That should be equal to rho B of P of A. That's all. This is interesting. It's like inner product. Okay? You know, I mean, this is like an inner product between these two, and you just interchange that. I mean, inner product, if you consider inner product as a linear function, this will give the same definition. So this is the definition. Okay? And if one of them is unital, then the other one will be state. I mean, it will take states to states. You can verify that. Okay? Easy exercise. You just write down the definition, it will just follow. Okay. So if phi is state preserving means it states to states. The star is state preserving is equivalent to saying P is unital. Okay. If one is positive, other one will be positive. That will be clear. Okay. So it will be state preserving. If I mean, if in phi is positive means phi of A star A is greater than or equal to 0. That same as phi of rho will be greater than or equal to 0. You can verify all those things. Okay. Just by definition, you can verify. It's an easy exercise. Okay. So this is the lemma we want to prove. Okay, I will prove it there. Okay, let me state the lemma. So this is something I have asked in the exam, but this is for more general, but the same proof is same. Okay. So phi is from A is the CP map. Okay, and phi is also unital. Okay. We have it's unital means the dual picture it's state preserving. Okay, it's unital. Then P of A star A is greater than or equal to P of A star P of A for all A. That's all. Okay, we want to prove this. So proof. So you want, let me write it. Want to prove P of A star A is greater than or equal to Phi of A star Phi of A for all A. Okay. So for that there is a trick. I consider this matrix A minus 1, A minus 1, 0, 0 star. So A minus 1, 0, 0 is greater than or equal to 0. Any matrix star is greater than or equal to 0. Okay. I mean, this is something, this is a matrix in M2C tensor A. This is an M2 tensor. I mean, you have matrix entries with entries coming from A. That is M2 tensor A. Okay. So M2 tensor A, this is greater than or equal to 0, just by definition. Any extra X is greater than or equal to 0. So this is greater than 0. So if you just write it, this is A minus 1 here, and that is A minus 1 here. A is 0, if you just add, so this implies A star A, and A minus 1, A0, then A0, my A star, so minus A star, minus A1. This is greater than or equal to 0. Okay, this matrix is greater than or equal to 0. This is in M2C. Now we know that one tensor phi from M2C to M1 tensor, I mean, from M2C tensor A is positive because phi is completely positive. This is positive. So phi of this you call this as X. Okay, now one tensor phi of X is just equal to phi of I use the letter phi, no? Yeah, phi of A star A and minus phi of A. See, phi is positive implies that phi is self-adjoint. I mean, phi takes positive elements to positive elements. So it will take any A is self-adjoint implies that A is equal to A1 minus A2, where A1 and A2 are positive. So if phi of A is equal to phi of A1 minus phi of A2, phi of A1 is positive, phi of A2 is positive, so phi of A is positive. So it will take self-adjoint to self-adjoint. So if we take any operator which will look like some A plus IB, where A and B are self-adjoint, so phi of that will be phi of A plus I times phi of B. This is self-adjoint, this is self-adjoint. So if we take the star, it will be, I mean, for self-adjoint, only here there will be minus. Okay, so because of that, it's clear that if positive map preserves star, it takes self-adjoint to self-adjoint, so it preserves star. So phi of A star is phi of A star. So similarly, phi of this is phi of A, okay, and it's unital. We have assumed it's unital, so phi of 1 is 1. Okay. So this is greater than or equal to 0. What does it mean by this is greater than or equal to 0? This just means that for any xi eta in, I mean, this A is contained in something. Okay, so you assume that this is contained in some MNC. So xi eta in MNC some Cn, I mean Cn tensor Cn, which is Cn direction Cn. Okay. I mean Cn tensor C2, sorry, C2 tensor A. A is contained in A acts on Cn. Okay. A is contained in Cn, MNC. A acts on Cn. Okay, so Cn direction Cn, which is MNC, I mean, which is C2 tensor Cn. Okay, that is where it acts on. I mean, that's how we have written in the matrix form. That's how we have written. Okay. So this implies that P of A star A, P of A star minus P of A minus 1 acting on any xi, any vector xi eta inner product with xi eta. This is greater than or equal to 0. This is the usual inner product. So you have to act on this element, you have to act on this element, you have to take. So this just implies that P of A star A, okay, minus P of A star, P of A star A minus P of A star A xi minus P of A star eta. Okay. This inner product with xi. plus phi of A xi. Okay. Huh? We can take it outside. P of A xi, then minus xi minus eta, okay, then eta. Okay, this is greater than or equal to 0 for all xi and eta, for all xi and eta. Okay. Now you can take eta to be, so I want xi, let it be xi. I want to prove that this is greater than or equal to 0. This minus this is greater than or equal to 0. I mean, this is greater than this means this, these are operators. This minus this is greater than or equal to 0. So whatever this minus this acting on xi, inner product with xi is greater than or equal to 0. That's what I want to prove. So I have phi of A star A, I have phi of A star. So if I put a phi of A here, so you can take eta equal to phi of A xi. Okay, so you get phi of A star, phi of A. Okay, xi, xi. So this, and you will get phi of, so you have phi of A xi here, you will get phi of A xi here. If you bring it here, phi of A star. So you get phi of A star A, phi of A star, phi of A here. So here you have phi of A xi, you have phi of A xi. If you bring it, you will get. So this will become 0. So this is, if you take eta to be this, then this implies phi of A star A minus phi of A star, phi of A xi, inner product xi is greater than or equal to 0 for all xi, plus 0, whatever you get. The second thing is 0. Phi of A xi, here you have phi of A zeta equal to phi of A xi, so you will get phi of A star. And here you get eta, phi of A xi, phi of A xi, which is again. So this is greater than or equal to 0. We are done. That's what we want to prove. We want to prove this is greater than or equal to 0. So this implies phi of A star A is greater than phi of A star phi of A. This is the definition. Okay. Hmm? Hmm. Yeah, it's good that you notice this. Let me plan this. Okay. The second lemma is we will use this. We don't use this lemma, which is like in the inequality. The second lemma is what is, we can call it as multiplication theorem so that we can invoke it again and again. So we call it multiplication theorem. I call it lemma because I'm going to use it to prove everything, but it's call it as theorem. Okay. So you have a phi from A to B, Cp. I don't think unital is not needed. Unital is needed because I'm going to use this. So unital, Cp and unital from A and B. A is in some MNC, B is in some MMC. Okay. Okay. Well, I don't see any finite dimensional thing about these things. Okay. This can be general also. Cp and unital. And suppose for some A, for some A, P of A star A equal to phi of A star P of A. This is greater than or equal to 0, but the equality holds in that. Okay. Then for all B, okay, this, I mean, I have used this, but B is coming from A only, okay? B is from A. P of A star B equal to phi of A star P of B. Okay. And there is no need for B of B star. You can take B itself because this is for all B. But I just for looking nice, I'm writing phi of B star equal to phi of B star P of E. this, I mean, the left side A and this, you can replace it with a B. This is the theorem. So this is for one single A if it happens, that for single A, for all B this happens. Okay, this is for all B. So in case this happens, this is true for all A, then it's a star homomorphism. That's what this says. And if E is positive, so it preserves star. It preserves the product if it satisfies this. So to check something is a star homomorphism, it's enough to check this. Okay? That's what this says. So corollary. If P of A star A, if the equality is satisfied in that inequality, but whatever the P of A star, P of A, then Phi is star homomorphism. Then Phi is star homomorphism. Okay, now let us prove this multiplication. Okay, so we want to use that inequality. So let you can take complex number, but here for our purpose real is enough. You take lambda in R, then P of A plus A is fixed, so and B is any B in A. Okay, in A plus lambda B star A plus lambda B. This is of course greater than or equal to phi of A plus lambda B star, or you can put it outside if you want. It's okay. And phi of A plus lambda. By the earlier lemma, this is true. Okay. So let's just evaluate. First one, A star A you get. Here also A star A you get. So you cancel it both sides. Okay. And the remaining thing we want to write. So this implies lambda times phi of B star B plus no, not B star B. B star B comes later. Lambda times B star A, A star B plus B star A, okay, plus lambda square into phi of B star B, okay, is greater than or equal to phi of lambda times phi of A star phi of B, okay, plus lambda times, okay, I can put it in the bracket. Yeah, I can put it in the bracket. Okay, I can put it in this bracket, plus phi of B star times plus lambda square times phi of B star phi of B. Okay, lambda is real, lambda not equal to 0. This is true for all lambda. Okay, so you can take lambda to be not equal to 0. So you can cancel this lambda, okay, and take lambda to be equal to 0. It's true for all 0. So you can cancel this lambda. This is true for everything. Then you can approach lambda to be 0 or whatever. Okay? This is true for all lambda. I mean, if you take lambda to be 0, both sides are 0. I don't take lambda to be 0. This is true for all lambda. So you can for positive lambda, so you can cancel this lambda. Okay? Not, lambda to be positive. Okay. Okay, you can take lambda to be positive. Okay. Then this is true. Okay, lambda to be positive. Now you can approach lambda to go to 0. It goes to 0. So this just implies that phi of A star A plus P of A star A plus P of B star B is greater than or equal to phi of A star phi of A plus phi of B star phi of B. Okay. I mean, since that is true for all lambda, this is true. Okay. 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 I mean, you can take even lambda complex number, but for our purpose, this is enough. Lambda positive. Okay. Now there is no lambda here. This is true for all A and B. So no, this is true for A and then all B. No, here this is A star B. I'm sorry. Oh my God, this is A, right? That is what we have. This is A. I have written A, B, A. Yeah, I have written everywhere correct. This is what we have. This is true for all B. Notice that this thing satisfied if you change A by IA. I times I is the complex number I times A, you get minus I here, and I times this, you get I here. I times I, it's gone. The same thing will happen there. So if you can replace A by IA, this is true. Same thing is true. Okay. So you can replace A by minus IA, IA, and B any B. So you can replace B by minus IB. Okay. Take A equal to A. I mean take A. I mean replace. The same thing is true for IA and IB also. Okay. Replace A by I times A and B by minus IB. Reason for taking minus IB is I want to get the minus sign. Okay. So then A star will become, if you take I, then you get a minus I here. And you have B, you have a minus I there, you have minus I there. Minus I into minus I is minus 1. So you get a minus 1 here. Similarly, you get a minus 1 here. Everywhere you get minus 1. So inequality is reversed. By taking A, replacing A by IA, B by IB, inequality is reversed. Okay. Yeah. Right. I think so. Yeah, correct. Right. So the inequality is reverse. Okay. Inequality reverse. So inequality. So it's equality. So equality. Okay. So equality holds. I have to write. So equality. Okay. So equal. Okay. So equality holds. Please write. Okay. Okay. So we have this equality. Okay. Now we have to get rid of that. I mean, we have to get rid of that plus. Okay. Now in this, you have this. I mean, you have this equality change means it is there is this is equal. That's what you have. Okay, you have the opposite inequality, so this is equal. That's what you have. Now in this, if you take B equal to IB, okay, I will come out. Here minus I will come out. So here I will come out. There minus I will come out. So this will become this. That is what you have. Right? By taking B equal to IB, by changing B equal to IB, you get a minus sign here. So this is true for plus or minus. By adding these things, you get it. That's all. Okay? IB, you get the result. Okay? Get the result. That's all. So we have proved this. Okay. Now, oh, I haven't changed the. No. We want to use that, not for corollary. Corollary is generally this follows from this, but we want to use this theorem as it is. For a single A, first not for single A, for many A's, if it is, I mean, for a family of A, if it is true, then for any B, this is true with that A. That's what we want to use it for this. Okay. See, if you have a computer or a Xerox machine or whatever, you have some information, some data, you can copy it. How you do? You have some, I mean, it's usually using bits and other things, right? 0, 1 or something. You have something. Then you get two copies of that. So classically, what we do is classical case is classical probability is given by omega 1, omega. You have a omega, which is where you have all your where you have encoded your data. Okay, then you want to get a map to omega cross omega. Okay? So you have some omega here. You want to reproduce omega times omega. Okay? For that, you need I mean, this is not how you do using the machine. It's not technology. Is not what we are discussing. Possibility in reality as a mathematical possibility. We are proving that it is not possible mathematically to clone something a quantum state. That will mean if that mathematical framework is, I mean, rightly explains the quantum system, then it is not possible in quantum system theoretically. Okay? Because I mean, quantum mechanics is a reality, which is a science, which is the mathematical framework explains that. Okay, if it correctly explains it, as far as we haven't seen any contradiction. Okay, if it correctly explains it, this should not be possible in reality. It should not be possible. I mean, humankind can never produce a machine which will copy a quantum state to another quantum state. So that's what this is. Okay, here I am giving a function. Doesn't mean you have to technologically you have to create some machine to do that. Okay, so that is possible. We know it's possible. We are copying email. We are copying everything. Images. Everything we are copying. Okay, so in general, if we have two sets, just a set, omega 1 or omega 2, which are sample space, okay, we take finite set. Infinite set also, it's okay. Okay, finite set. Then if we have a function from here, omega 1 to omega 2, then you have, if you have just function, so this is a finite set, this is a finite set. You can take infinite set also, no problem. Then you can have a df from c of omega 2. You can take continuous function if you want, or any function. Here all functions, because it's finite. So C of omega 1, where Tf acting on any G, okay, maybe I call this F and G, we want, okay, I call this R. Okay, R is a function. Then Tr from here, Tr of F at G, so Tr should land here. Okay, so at omega 1, okay, is equal to G of R of omega 1. Okay, F of, yeah, this is G. G is a function. I mean, this is omega 2, no? So G is a function in C of omega 2. G or G at omega 1. Okay. TR is a function. You take a function. TR is a map from C of omega 2 to C of omega 1. You take a function here to function here. So TR of G, a G is a function here. TRG acting on omega 1 is G of R of omega 1. Okay. R of omega 1 lands in omega 2, so it acts as a function. Okay. So for any function from omega 1 to omega 2, we get a map from here to here. This TR is a star homomorphism. You can see that this is a TR is a star homomorphism with respect to point-wise product. Okay. With respect to point-wise star and point-wise product, the usual one, what we define on C of omega 1. This is clearly star homomorphism. Okay, we can see. Okay. So, I mean, let's come to, I will come to that, how to define self-adjoint, how to define random variable in general. We have defined random variable as a self-adjoint operator. I gave some reason for that using vectoral theorem. The same thing we will do it again. I will say it again. So here I want to have a map from here to here. So it is equivalent to, so the map will be, of course, the map is going to be omega going to omega. That's all. You have a map. Okay, this is the copying map. Just omega going to omega. So what will be this map in terms of, so this is a map, you call it as I or something. Okay. Then Ti, yeah, Ti from C of omega cross omega, which is C of omega tensor C of omega. Okay. The same definition will, in finite dimension, it is easy to verify. C of omega cross C of omega 1 cross omega 2 is same as C of omega 1 tensor C of omega 2. Okay. The same finite, it's finite dimension, we can easily verify all this. Okay. So C of omega 2 to C of omega. So that's what you, so this Ti acting on some F, okay, at omega, which is going to be F of omega, the diagram. Okay. So you can copy. I mean, this is the copy in terms of set theory. This is in terms of functorial. This is the functional picture. Okay. So what we have, what we need in quantum setup, we want a map, want a field, okay, from. So we want a map from forget about that. in general, we want a map, phi A star. Let me first define actual cloning. I mean, this is similar to this, but this is the covariant picture or something. But I will define it here. We want a map phi star from A star. Okay, you want to clone some. I mean, here you have cloned some omega to omega omega. Okay, you have just copied it. Okay, there is a copying process is there. So here you want to have a row. You want to get two copies of row. That's what it means by cloning. You want to get another copy. It's not just that. I mean, that is possible. You can teleport some row to somewhere. Those things are possible. But you can't get a copy of it. You can. You are not. Once you get another copy, you can make a copy of. If you have a row here, you can make a copy somewhere. Okay, it's possible to copy, but this will be destroyed. It is not possible to keep. You can't keep both the copies. Okay, that's what no cloning theorem says. Okay, there is something called teleportation. You will see later, where you can send from here to anywhere. You want to Andromeda galaxy or something, provided you have a entangled pair there. Okay, then you can we'll prove that. Okay, so if you have some quantum state here, you can send instantly. That's not instantly. I mean, there someone should do something to get that. Okay, so that will so far that you need to send through telephone or something. You have to tell them, and they have to do something. So that will take time. Okay, so it's not instantly. I mean, it will take million years or something to take it to Andromeda galaxy. So what I was saying, so it's possible to send a copy. You can copy, but the original copy will be destroyed. We cannot keep both. You cannot keep. You cannot keep the. You can send the quantum state is something you can see. The another thing we are going to see. You cannot measure a quantum state. I mean, you can measure something. You don't get all information. By measuring, you get some information. From that information, you cannot get back the state. So that is also another theorem we are going to prove. Okay. So we didn't prove all these things. So that's why I'm doing. Okay. We had not done enough on CP map. So that's why I'm doing now. Okay. So it was boring. I mean, it was doing too many things without doing communication. So I postponed it. So I'm doing now. Okay. So if we have, the thing is, if we have, so this is the actual cloning. You have A star to A star, tensor A star. Okay. This is a finite dimensional space, finite dimensional. Okay. And this map should take a row. I mean, usually cloning theorem will say that you take row to row tensor row. Even I am not saying that. This takes row to some chi here. But if you take trace out here, trace out that, what is trace out means? So this is how I defined partial trace. See, when you have a state, this is general, not I will come back to this. If you have a chi in A star, tensor B star, okay, then one tensor trace, this is the partial trace, I call it partial trace. I mean, there is no, I am not using any trace here. I mean, there may not be unique trace. There will be a trace, but because it's finite dimensional, there will be a trace. Whatever trace means it's a linear function satisfying some property. Okay, but in 2-1 factor you have a trace. It's like that, but it need not be unique trace or something. We are not working with the trace there. But by this I mean, or even if you take one of them to be complex number C, this will be actual trace. Okay, by one tensor trace acting on chi is just chi acting on so one tensor trace is a functional acting on one. It's only acting on A. You are tracing out this. Okay, so this is acting on A is equal to chi A tensor 1. That's all. This is the definition. This is how, if you remember, this is how I defined the partial trace even for M and C. Then we showed that is actually the partial trace we defined through orthonormal basis and other things. Okay? I showed this is how I first defined to show that it does not depend on orthonormal basis and other things. Okay, the actual definition of partial trace which we have been using depends on orthonormal basis, but does not depend on orthonormal basis is because the definition is given through this. This is through, I mean, there we use Rees representation theorem to get that. Okay, but in general, partial trace, or this can be called as conditional expectation if you want. Okay, this is conditional expectation. You have A tensor B, you just get the condition, you just take the conditional expectation onto A. That's what it means, and this is exactly this. Okay, so which I call it as one tensor partial trace. One tensor trace acting on chi, so it has to act on this A, which is this A acting chi acting on A tensor 1. So this is contained. This is acting on This is operators on, operators on A tensor B, right? Not operators, linear functions, sorry. A tensor B star, okay? Equal to, sorry, that's equal. Okay. K of A tensor 1. K tensor 1 sits there and it has. Okay. So this is what one tensor trace is. So here cloning, by cloning what I mean is, so this is just to recall. By cloning, I mean I want a map. I mean cloning means you have to have a machine which would copy any row, not some particular row. Okay? That's not we are talking about. So you take any row here that should map to some chi. If you take the partial trace onto A star or this way or that way, you should get row. That is what cloning is. Okay, so you have a phi star from row to chi such that one tensor trace of chi equal to trace tensor 1 of chi equal to rho, whichever the way you take. Okay, that is equivalent. The same thing as saying P star of any row. Okay, that will go there. P star of row, then one tensor trace is equal to one trace tensor 1. This is the partial trace on the next one times phi star row, okay, equal to rho itself. Okay, this is what we want in the quantum setup. Cloning means this is what we want. We want to show this does not happen, or if it happens, the algebra has to be commutative. That's what we want to do. Okay. Okay. So we first exactly. No. This you are taking A star to this. Okay. Then you are taking conditional expression back. It is just that you have one copy of this. You have a product state. You not product state. You have a state on this tensor product. A bigger. You have an amplification. You have a bigger state. Okay. That state, when you take conditional expectation onto this, should give rho. That should give rho. Okay. If you take conditional expectation, you will lose the information on the other one. That's not the point. Here, from rho, you are getting some bigger thing. It's for example, rho going to rho tensor rho is such a state. Okay, then that will not be given by a map. C star map. That's what it says. You can take rho to rho tensor rho, but here this is a much stronger statement. In general quantum information theory, usually, as I said, you will take one single chi. You will take to tensor some for a fixed field. It will be taken by a unit. The proof is just very easy. It will follow immediately. Here also it will follow immediately. But we are just having a theory, a nice theory behind it. That's all. So the situation is clear. You want to have a map from A star to A star tensor A star. You have a phi on A tensor A. Okay, such that if you trace out, if you take the conditional expectation on the first one, you get rho. Second one also you get it rho. So that is what is this. So you want to write the covariant version of this. You want to get. This is equivalent to saying you get a map on that. Okay? So what is the one tensor trace star? Can you guess what is? One tensor trace is a map in general. Not for this A tensor A. This you have A tensor B. Okay? Then you can take one tensor trace. This is a map from here to A, right? One tensor trace from A star to A star to A star. So now we want one tensor star, one tensor trace star, okay, which is a map from A to A tensor B, right? What is that map? It's in the definition. A to A tensor B, what is the map? There is not too many maps are there. It's just A going to A tensor 1. Is there any other possibility? Right? What is it supposed to satisfy? This is the star of this. Okay, this is one tensor trace is a map from here to here. This is the star of that. Okay? Star means, I mean, this star, whatever, the star between these Banach spaces. Okay. So what is it supposed to satisfy? So what do you have? You have one tensor, I mean, you want to have phi of one tensor trace star should be equal to that, right? If one tensor, let's write one tensor trace. I want to talk about one tensor trace. One tensor trace of chi equal to some row. Suppose not this row, some row. Okay. Then you want to talk about one tensor trace star. One tensor trace star is A tensor 1, I am saying. Okay, A tensor 1. So you want to talk about, so the star should satisfy chi star and not chi star. I mean, star should satisfy one tensor trace star. Okay, this should act on A. Okay, so that will go there. It should chi should be equal to one tensor trace acting on chi. Okay, that will give you something that should be equal to, right? Right. This is the definition. Okay. So if you put A tensor 1 here, if this is A tensor 1, one tensor, yeah, if this is A tensor 1, chi of A tensor 1 is precisely equal to one tensor. This is definition, right? Chi acting on A, right? This is the definition of a partial trace. Chi is a state. One tensor trace acting on A is chi of A tensor 1. That is how trace is defined. Partial trace is defined. So from the definition, you just write the definition, it follows. Okay. So this is just to tell you that the one tensor trace, its star is A tensor 1. Okay. Once if you are convinced, I erase this. Now we want to use this. Okay. So we want to let contravariant of this. That it just says that phi tensor phi of one tensor trace. I mean, we have a phi star from A star to here. Okay. Then phi is from A star tensor A to A. Our cloning map is phi star from A star to A star tensor A star. Our phi should be from A star tensor A to A. And it satisfies the following. You have to take the star of this. So it will be phi of one tensor trace of, so rho will come here, right? Rho of this A equal to rho of A. Okay. Right? I'm just applying it on A. Okay. Right? Okay. So this just implies that P, I mean this star, sorry, here there is a star, one tensor star. This just says that P of A tensor 1 should be equal to A. That's all. Okay. So we want a map. So this is the theorem, no cloning theorem. This map is not possible. That's what we want to prove. Okay. No cloning theorem. The theorem says the following: A, B are algebra, phi from A to B. Okay, A, B are some algebras. Okay, P is CP and unital. Okay, such that, sorry, not yet. A tensor A to U. Okay. I mean, and also you can use one tensor A also satisfies the same thing. Okay. So if you have a phi from A tensor A to A, which is CP and unital, okay, map is unital, such that phi of A tensor 1 equal to A is also equal to phi of one tensor. Okay. Suppose there exists a map, CP map, unital CP map which satisfies this. Okay, such that phi of A tensor 1 equal to A equal to phi of one tensor A. Then A is abelian. Difficult, right? Hope you can read. Okay, then A is abelian. This is the, I mean, the situation is classical. Abelian means it is C of omega for something. I will give you a video where it is proved, which is just Kelvin theorem. It's the same idea, but in finite dimension, it's very easy. That's all. Much easier. Okay. The proof is very easy. We have to remember this multiplication theorem. Okay, the multiplication theorem says the following: phi of a star a equal to phi of a star phi of a for some a. Then for all b, this is okay. We will use this. We will use this theorem again and again and again and prove many quantum impossibilities. It's because of this. So you can see that phi of a star a equal to phi of a star times phi of a cannot be satisfied, okay, for many operators, for a large class of operators. Okay, so proof. So what we have is the following. P, I am just rewriting here. P of a tensor A to A, such that P of a tensor 1 equal to P of 1 tensor A equal to A. Okay. This is the star of the cloning map. Okay, it satisfies this. Okay. Then you want to talk about A star A inside this. Okay. Now phi of 1 tensor A star 1 tensor A. Okay. This is equal to phi of 1 tensor A star A. Okay. This is for all A. Okay. Equal to 1 tensor A star A. So this will be equal to A star A only. Of course, this is A star times A star. So this is phi of 1 tensor A times phi of 1 tensor A star. Okay. So phi of 1 tensor A star, 1 tensor A equal to this. So 1 tensor A satisfies the condition of the multiplication. 1 tensor. Okay. So this implies for all B, you can, I mean, in multiplication theorem, I am replacing A by 1 plus 1 tensor A. Okay. Then for all B, for all B in A, I apply it for the operator B tensor 1. Okay. I mean, I apply for B tensor 1. Phi of B tensor 1, B tensor 1 or A tensor, yeah, B tensor 1 star. I don't take star. B, I mean, by replacing B by B star, I don't need to take star. Okay. B tensor 1, 1 tensor A. Okay. Similarly, A star also satisfied. Do I need that? Maybe I don't need. This is equal to B tensor 1, 1 tensor A is equal to P of B tensor 1 times B of 1 tensor A. Correct? That's what we have. For all B, that is true. Okay. So in tensor, it's true for B tensor 1. Okay. That's equal to this. Okay. Now this is also equal to phi of one. These two commutes. They are in the different tensor component. 1 tensor A times B tensor 1. This is equal to B tensor A basically. This is B tensor A. B tensor 1 times 1 tensor A. If you compose as operator, B tensor A, which is same as 1 tensor A, B tensor 1. You can write. By the same thing, you can apply for. But I need A star here, right? But this is true for all A in A, so I can use A star also. I can replace A by this. So this is equal to phi of phi of B, I mean phi of B tensor 1. This is equal to phi of B times phi of A, right? Sorry, A. This is equal to BA. This is just BA. Now this is equal to phi of 1 tensor A into phi of B tensor 1, which is equal to AB. So AB equal to BA. That's all. And these two are equal. Phi of B tensor 1 times 1 tensor A is same as 1 tensor A times B of A. These two commute. So these two are same. Okay. But this is by whatever multiplication theorem we have, this is equal to BA. And we are using this cloning condition also, which is equal to BA. If you use the same condition, you get AB. So AB equal to BA. So it's abelian. That's all. Proof is very easy once we have the multiplication theorem. So this says that you cannot clone a quantum state in reality. Mathematically, it's impossible. Okay? Certainly, physically also, it's impossible. Okay? I mean, you get physical impalpability through mathematics. You guess it through mathematics. Okay? You can't go faster than light is a theory, but you haven't checked it. I mean, there is no way. It's mathematically not possible. Okay? I mean, when you assume all these things, when these things are consistent, this theory, mathematical theory explains that, then it's not possible. Okay. Okay. So next view, I want to say that you cannot code a quantum thing, quantum information through classically. Okay. So that is, if you have some quantum row, for that you get some information from a quantum state, whatever the information. Okay. From that, you cannot go back and construct the quantum thing. That's what we want to say. Okay. So for that, what does it mean? You have, so this is coding and decoding. Maybe I call it C from some A to B. Okay. A star to B star. Okay. Where this B is commutative. Okay. Then you have a D from B star to A star. Okay. Such that which one you compute? D of C. C is from A to B. Then you oppose this. So it will from A to A, right? Yeah. A star to A star. Okay. Now suppose this is equal to identity. Okay. If this is identity, then I mean this may be clear to you. See, the thing is, if you have A is an algebra, B is an algebra. Suppose you have algebra. If you have a star homomorphism which is bijection, or if, I mean, this just says that, this doesn't say that there is bijective. It just says that it has one side inverse, left or right. I'm always confused with left and right. Whatever, left inverse. No, this is left inverse, right inverse. This has a left inverse, right? Okay, whatever. Okay, I have to check with which is right hand, which is right left hand. Okay, so it has one of those inverse, one side inverse. Okay, but this is not a star homomorphism. You should remember. If you have two algebra, if it is star isomorphic, if there is a homomorphism which is also a bijection, then they are same, of course. Okay, but here that is not it saying. You have a CP map. Okay, you have a CP map from A star to B star. You have a CP map such that you compose those things, you get an identity. Then B is commutative, then A is also commutative. I mean, A star. A star, there is no meaning for A star commutative. A star is also classical. I mean, A star, I will frame it in the covariant version. A star is, I mean, it's a probability measure. Okay, commutative means it's classical. That is the following theorem. This is what the following theorem. This is no coding theorem or something. Okay? If you have a phi from, so here I want from B to A, okay, and this from A to B, such that phi of phi, which is from B to B, okay, is identity. Okay? Then, okay, and B is abelian. Okay? Then A is also abelian. You have a CP map from a commutative C-star algebra into A, and you have the reverse map. This is the one coding map, and this is the reverse map, decoding map. Suppose you can decode, then that has to be identity. That's what this is. Can you catch 6 o'clock vehicle? I will take a long time because I missed the last class, so it will take some time till I have energy. Okay, proofs would be easy. You just have to. So what do you have? We have two map, P and chi, P from here to here, then chi acting on P. Correct. Now, let's take A star B. Doesn't matter. I mean, A B we can take, but I'm taking A star B, which is equal to chi of phi A star B. I mean, this is uh, chi of B from B to B or A to A. Now, from C, we should get a map. If we have a row, from that we get a B, and from that we should construct this. So this is correct. Such that D of C is identity. That's right. So it should be this way, correct. Are we going to use B star E? B star E. Okay. And this is greater than or equal to E of E of. I mean, it's all positivity preserving. So, right? Because this is phi of S. I mean, you forget about this. Phi of A star A is greater than this by our earlier lemma. So then this is positivity preserving. So you can write it like this. Okay. And where is A? A is in A or B? Phi is from B to A. So yeah, this is okay. A should be in B, no? If this is the case, A should be in B. Then I may not get the right thing. Let's see. Let's see. I have to use this multiplication theorem only. So this is greater than or equal to this. And that is greater than or equal to chi of, I mean, this is again this star this. Again, I use the same thing. P of A star chi of P of A. Okay. And this is equal to A star. So everything should be equal. Okay. And similarly, A star is equal to chi of P of A star, which is greater than or equal to chi of P of A star A star A of A. Okay. And if B is abelian, then I want to show A. This is in B, no? Hands up in B. You can get it from A to A. Okay, let's say this is also same as chi of P A star, chi of P A. So this is equal to A star. So they are all equal. Okay. This in particular says that these two are equal. Okay. These two are equal. I mean, this is equal. Since it is abelian, these two are equal. Okay. One is these two are equal. P of A star P of A. P is a map from phi of yeah. So what should be the right statement? This is from B star to this. Oh, this is from A to B, right? No, this is from A star to B star. So this is from B to A. this is from A to B, such that oh, you are saying phi of chi should be 1. So let me just get it right, and then so this should be that phi of chi should be from A to A should be 1, right? Is that, I mean, here we are here we are getting from A star to A star. So he will get from B star to B star only, no? No, that should be from again A to A only. Sorry. We have a map from A star to A star, so we will get from A to A only. Right. So this is the statement. Okay. Yeah, this is so the map we want is one second. So chi phi of k, okay, from A to A equal to identity. Okay. Yeah, if you use the covariant version, this is what you get. Good, thank you. Yeah, this is what you get. Okay, so then I change everything. Okay, and there is nothing. I mean, you just change. This is changed to P of chi, right? P of chi, okay, and P of chi of A, chi of A star, chi of A. Okay, do the same thing. Yeah. Okay. That is equal to A star A. And similarly, you get this. Okay. I mean, similarly, you change here. Okay. Change to, I mean, chi of E to phi of chi. You just change it. Okay. If you change all these things, you just get A star equal to A star A for all A in B. This says that every element is normal in A. Okay. If every element is normal, it has to be commutative. Is it clear? Oh, it's clear. Huh? Every element is a normal element in a even in C-star algebra. Not C-star algebra, here it is in finite dimensional algebra. Finite dimensional star algebra, every element is, I mean, it's in matrix algebra. You can assume spectral theorem. So it says that for all A in A is normal. Okay, we can assume A is contained in MNC. Okay. Then A will look like summation lambda I B. Right? You have another B which will look like summation mu I Q I. Okay. So this is in A. This is in A. Okay. Then Pi, Qis are in A. Is it clear? Is it clear? Why is it clear? If you have A, then any polynomial of A is there. Okay. Now you take P of x is equal to x minus product of x minus, you take Pi, x minus lambda j, where j not equal to I. Okay. Now this will be 0 for every lambda I, every lambda j, except lambda I. Lambda I is not equal to lambda j. Okay. So Pi of lambda j equals 0, and Pi of lambda I is equal to x minus lambda I. Sorry, which is just some product of lambda I minus, which you call it Pi of lambda I, which is not equal to 0. Which is not equal to 0. Now you divide it by this. Okay? I mean, if you have an operator in an algebra, then it's polynomial. Any polynomial of that is in that algebra. So you have that Pi of, I mean, you have this Pi of x is there. I'm just saying that Pi of this A divided by the number Pi of lambda I, which is not equal to 0, is equal to that projection. I mean, this P is small p, okay? Small p. I mean, this is the polynomial P, that is the projection P. Okay? That is equal to that PA. So you get PA as a PA in that. That is how we get PA. Similarly, QA is there. So it is enough to prove that A and B commutes. It's enough to prove PA and QA commutes. Okay. So if you have but then PA QA, so it is enough to prove the following. I mean, all I'm doing is if A star A equal to A star, all elements are normal, then it is commutative. That's what I prove. So it's enough to prove P, Q in A, and PQ is also normal. Okay. Okay. Then P and Q commute. That's what I want to prove. So PQ is normal means what? PQ QP, its star is QP, okay, is equal to QP PQ. Okay. So PQP, I mean, I can see this proof only. QPQ. Okay. I want to say they commute. From this, it's clear. So suppose you can write P as this. Okay. And Q as P1, P2, P3, P4, which is a projection. Now, this says that, I mean, PQP equal to QPQ. Okay. This implies that, I mean, this PQP, PQP is a projection. PQP equal to P, I mean, PQP, PQP, if you take it. Okay. This QP, this is equal to P, PQP, which is equal to PQP. So PQP is a projection. If you use this condition, PQP equal to QPQ, this implies PQP is a projection. PQP is just this P1. This P1 is a projection. Okay, this will be only P2 star. For this to be a projection, this should satisfy P1 square plus P2 star P2 equal to P1. But P1 is a projection means P1 square equal to P1. That means this has to be 0. This has to be 0 means P2 has to be 0. So these two entries are 0. That means it will commute with P. If these two entries are 0, then it will commute to this, as in the matrix form. Okay, this is the proof. Okay. PQP equal to QPQ. No, that is because PQ is normal. P is projection, Q is projection. Okay. All elements are normal. PQ, the product is there in the algebra. In the algebra, everything is normal. So PQ is also normal. So PQ is normal means PQ, QP is same as QP, PQ. Okay, whatever. A star A equal to A star. Okay. So from that I get this. So from that I get that PQP is a projection. You can use that. PQP is a projection means this P1 is a projection. Q, you write P as 1001. Any projection can be written like that. You write Q in terms of that. If you write Q in terms of that, you get P1, P2, P2 star P4. Okay. And this is a projection. This is what is PQP is. Okay. This is a projection. If that is a projection, this has to be 0. Okay. From that it follows that they commute. So P and Q commute. Because P all spectral projection commute, any two operators will commute. So from that it follows. Okay. So it's an abelian algebra. Okay. So I have proved it became 5. I want to prove uncertainty principle. I will do it tomorrow. Okay, it has become 5. Right time, no? Huh? Yeah. But I will take another half an hour. Okay. Maybe I will take or I will do tomorrow. What do you think? Huh? You're fine with that. You're also fine. Okay. Then I will do that. I mean, till my energy, because I missed the last class, I will do this. Okay. So this is about no cloning theorem. This is no coding, no classical coding theorem. These are the two theorems. Then the another impossibility is uncertainty principle. In physics, you must have learned uncertainty principle. Uncertainty principle says that if you have two things, you can't measure both position and momentum precisely as, I mean, anything you measure as precisely as you want. You cannot measure anything precisely as it is. Even the length of in reality, even length of a line, there is no notion which says that this is the length of it. For example, if you have a length of one right angle triangle, if the length is 1, and even that 1 is not clearly 1, you call something as 1, you have another side as 1, then the diagonal will have the length will be square root of 2. But square root of 2 is an irrational number. How will you measure? You cannot measure, right? You cannot, you will go on, you will keep on measuring. I mean, as in reality, it's not possible. There is always a problem with when you go to smaller thing. It's philosophically also there is a problem. But mathematically, we assume that those things are, I mean, we think we can handle. But in reality, there are a few things which can, I mean, mathematics need not be reality. Okay? So in reality, it not be possible. Okay. So here the thing is, I mean, it's only as precise as you want. Okay? Up to some, in reality also, whenever you do experiment, you measure things up to some error. Okay? The error can be very small as you want. So given epsilon, whatever the epsilon, so small, you can do something. That's what it says. So if you can measure a position of some particle, then you cannot measure its momentum and the velocity, which is equal to velocity. So you cannot measure its velocity. As precise, if this precision is, this is like, if you know Fourier analysis, if you have done Fourier analysis, if f goes to somewhere 0, that the other one, Fourier transform, will blow at infinity, something like that. Okay, this is actually the position. If you so I'm not going to, maybe I will state it in the next thing, but we haven't done that. So usually you take L2 of R. This is your Hilbert space H, which is an infinite dimensional Hilbert space. There, the position operator, momentum operators are given by this. You have u. No, you have already know this Weyl operator. This is the logarithm of the Weyl operator. It's not, these are all unbounded operators. Okay. So if you can define T of any f at T equal to f of T a plus T. Okay. And another one is the differentiation or something. I mean, you can define it as this is the translation, which is unitary. You have, for each a you can do, each a in real you can do. You have to take the, so this is the differentiation. You have to take its generator. I mean, this is TA equal to e power I some PT or whatever, PPA, whatever. Okay? There will be an operator, unbounded operator, which will determine. That P is what is called position operator. Yeah, this will give to differentiation. That will be differentiation, which is an unbounded operator. So similarly, if you have the e power IAT, if you multiply by that, you take the derivative of that, you take the generator of that, that will give you the momentum operator. They will have a commutation relation, which is the Weyl commutation relation. Okay? So uncertainty principle can be defined through that, and I will come to that later. Here we are doing algebraic one using CP math. That's what we want to do. Okay? Here the statement we want to make is joint measurement of two random variables is not possible. If it is possible, then it has to be abelian. That's what we want. Okay? So before that, I have to say what is a measurement. We have defined measurement for a random variable. If you have a random variable which looks like summation lambda I pi or finite dimensional summation lambda I pi, then a measurement of this will give you a lambda 1 up. These are its eigenvalues. Will give you a probability distribution on this. Okay, this will x will take the value probability of x equal to lambda I. Okay, probability of that equal to, if your state is rho, then trace of rho x. I mean rho p, the pi. So pi. Okay, that's what you trace of rho x will be the expectation. Sorry, trace of rho pi. This will give the probability. And there is a collapse thing that says that it will collapse after that. That's a theorem. It's not mathematical. Okay, the collapse postulate is a theorem. I mean, it's not a theorem. It's a postulate. Okay, it's not a mathematical theorem. We proved it. It's an assumption. Okay, so but we don't want to use this. You will come to this. This is same as that. I mean, this says that if you have any random variable, self-adjoint operator, if you have a state, you get a distribution. You get a probability distribution on its eigenvalues. Okay, that is what measurement is. Okay, so for us, a measurement is you want to get some classical information from a row. Okay, that's what a measurement is. Okay, so let's use M. M is a map. So you have A star. It's all, you have a row A star. Okay, from here to A star tensor B, B star, where B is commutative. Okay, you have a commutative algebra. you have star of that, which is of course probability measures. Okay, then you have a m from a star to a star. This is what is measurement for us. Okay, so we get a probability distribution. Given any row, you get something like this. Okay, now suppose you take the partial trace on this, so you get something here. Okay, suppose you get row back. The point is you can't measure anything without altering the original state. If you measure you have a quantum system, it is in some state, quantum state. If you measure, that state will be altered. That's what the Van Neumann collapse also states. That's also it states. But we are going to prove that. Okay, so if you have a row here, so then m of row will come here. Okay, suppose 1/10 are trace. You take the partial trace. You take the partial trace on this. I mean, you get a state on this. Okay. Now, if you take the partial trace on this, you get the probability distribution. If you take the probability to partial trace on this, you get some row. That row cannot be this row. I mean, this cannot be. This cannot happen. This is what it means that it has an unchanged. Okay? It is the same thing. That's what it means. Okay. So if this happens, okay, then you haven't got any information. That's what we want to say. That means if you get any information, the state will change. You want to prove that if you get any information, if you get some reasonable information about rho, then the state will change. But here we say that if you state hasn't changed, that is, it is rho itself, then you haven't got any information. Then I want to say that 110, I mean, this 110s are, I mean, what is this? Then one trace tens are 1 of this row, which is the probability distribution, is mu for all row. That means, I mean, you get the same mu for all row. If this happens, if this happens, this is what I want to prove. You measure it and get the row, and still the row is unchanged. Okay, I mean, these are all CP maps. I mean, we do something. Measurement is also a CP map. Okay, so we do. It's an operation. If we do an operation and we get back the state, then you haven't got any reasonable information because this mu is same for everything. Okay, that's what this says. Okay, so what does it mean by what is the covariance statement of this? This is equivalently, we have a m. This is m star. Okay, I'm calling this as m star. Okay. I call this m. I'm calling it as m star. Okay. Then you have a m is from A tensor B to A. Okay. So I want to write the contravariant statement. The trace star one sum, it takes a I want to say that no, I will prove a statement which will imply this. Okay. Let's write a theorem. I'll prove a theorem which will imply that. Okay. But this is what we want to prove. Okay. 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 The theorem is the following. Let m is from A to A tensor B to A, okay, where B is abelian. We don't need the abelian. Some B, sorry. We are, I mean, abelian means it will have something. We are moving more general. We don't need abelian. Okay, A tensor B to A. Okay, then such that m of A tensor 1 equal to A. Okay? That is what this statement. I mean, you can convert this statement. M tends to M star. You take, I mean, this is M star. Okay? M 1 tensor traces A tensor 1 of row of A should be row of A. That should, I mean, this is for all row means it should be equal to this, right? I mean, if row of B equal to row of A, then A equal to B. Okay, because of that. Okay, from we are using that factor. Okay, states separate the points. Okay, so this is the statement. This statement is equivalent to this statement. So then I want to prove this statement. Then m of 1 tensor B equal to is in A intersection it's in the center. Okay. Okay. I mean, this thing should be possible when it is commutative. Okay. So we want to assume that non-commutativity, high non-commutativity to prove that. See, the thing is, if A is commutative, this should be possible. There is no problem. Okay, I mean, commutative means you can actually that state itself is a classical state. There is no, I mean, you cannot say that you cannot do any measurement or something. Measuring it will not alter. So if A is partially commutative means A is direct sum of something and it commutes, sum of element commutes, then also something should be possible. That is what this statement says. So in particular, if A is a factor, if A intersection A commutant equal to C times 1, if it is a factor, okay, then this says that M of 1 tensor B should be a scalar, right? And that scalar gives a map. It should be a scalar, which will depend on B, of course. That scalar has to be a map, and it will be a linear map, and it will be positive. It will take positive to positive. So this is equal to some P of B. And I have used P of B times 1. Okay, where phi is a state. A to C is a state. Okay, this is the statement. I mean, this statement implies this. If I prove this statement, that implies this. If it is a factor, then this is true. Fact A intersection A prime is a scalar, so it has to be a scalar, and that scalar will depend on B, and that will give you a state. That function will give you a state. So that's what this is. Okay, so I have to prove this. So if I prove this statement, he is going from sorry, B to C. Correct. You are right. Sorry. Yeah. This is just a linear functional on B. Yeah. Yeah. No. B to C. Correct. Yeah. B to C. Yeah. Correct. This is for all B. Yeah. Okay. 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 So if we prove this statement, okay, this is equal to phi of B. That is same as this, right? That phi is a measure. That phi is the mu. Okay. If we want to call it mu, I call it phi. That is mu. This says precisely this. Okay. If you use the the other version of this, dual version of this, it is exactly this. Okay. So this is what you will prove. Okay. And the proof is very easy. Only the formulation is like this. Formulation is difficult. It's not difficult. And formulation has something. The formulation is non-trivial. The proof is easy. Again, we use the same multiplication theorem. The same thing will work. Okay. We have what? We have M of A tensor 1 equal to A. Okay. Now we want to prove that M of 1 tensor B is it commutes. I mean, A tensor B, it should commute with anything in A. Yeah, M of 1 tensor B should commute with this. Yeah. We want to prove that M of 1 tensor B commutes with anything in A. That's what we want to. So times A. Okay, is equal to M of 1 tensor B times M of A tensor 1. Okay. Again, the same thing is true. M of A tensor 1, A star tensor 1, M of A star A tensor 1, tensor 1, which is equal to A star A, okay, which is equal to M of A tensor 1, A star tensor 1, M of A tensor 1. Okay. So by multiplication theorem, this is also you can do. Okay. By multiplication theorem, this is equal to M of 1 tensor B into A tensor 1. Okay. Which you can bring it, these two commute, which is same as m of A tensor B, which is same as m of, I mean, A tensor 1 tensor A times, I mean, A tensor 1 times 1 tensor B, by the same thing. Okay? So this is same as m of, I mean, you can directly write A into m of 1 tensor B. Okay? So m of 1 tensor B commutes with A. Okay? This thing implies m of 1 tensor B, then m of 1 tensor B commutes with A. Why is it in A? No, m of 1, that is the definition. No, that's the definition. That it goes to A. It is in A intersection A. Yeah. So we prove. Okay. So this is one version of uncertainty principle, but this is not what we want. We want to prove something about random variable. So the most general version of random variable in quantum probability is just, it is a star homomorphism between any two algebras. The reason is the following. See, so a random variable is from one set to another set, one probability space to another probability space. You forget about probability measure and other thing. If we have a function from R from omega 1 to omega 2, okay, then you have TR, we have already seen T of from C of omega 2 to C of omega 1. Okay? And this is a star homomorphism, right? So a random variable, I mean, in most general, random variable is usually real valued and other thing. Okay? So a random variable, you can say that it is a star homomorphism from B to A. It's a random variable taking values from A to B, basically. I mean, it's a random variable taking values, a function from taking omega 2. Random means you need a probability measure and everything. It is just a function from omega 1 to omega 2. There is no set here in quantum probability. So that is a map from here to here, star homomorphism from the reverse map. Okay. So similarly, you have a star homomorphism B to A. This is what is a random variable. So when one of them is B is C of omega. Okay. So a usual real random variable, whatever, is just a real random variable, is a map phi from C of omega to B. A star homomorphism. Okay. This will give a phi star from here to here. That is means it gives a restriction. If you have a state, you compose the state with this homomorphism to get another state on the image. Okay, that will give a restriction of the states. Okay, anyway, we don't need all that. If you just look at it, it will be clear. Okay, so we have a homomorphism from A to B. Okay, then using that thing, you get a restriction of the states of one algebra to other. That is what the dual version will be a restriction basically. Okay, that will give a restriction. Okay. Anyway, so for us a random variable is a star homomorphism C of omega to A. This is actually given by self-adjoint operator. How it's given by self-adjoint operator? So this is the proposition. Any P from C of omega to whatever A, okay, is bijectively determined by a self-adjoint X in A by P of P is from here to here. This is not one map, this is that I map, identity map. P of I equal to X, where I is from omega to omega is contained in R. Okay. We want omega is a finite set in R. I mean, we want self-adjoint operator. Omega cannot be any set. Okay. So omega C of I of omega to I is a function. So we need a function here, I omega to r, just the identity function. This is just the identity. Okay? I mean, I of lambda I, these are lambda I. Those lambda I say will be the exactly the, what is that, eigenvalues of x. Okay? Proof. One way, if phi is something, then phi of I mean, you can see that, and phi of I is x. Okay? You get phi of I equal to x. You get a, if phi is from C of omega to A uh, is a star homomorphism, then phi of I equal to x. This is how we get self-adjoint operator. Or you can use spectral theorem in the general sense also. If phi of I equal to x. Here also we are using that. Phi of I equal to x. That's what we get. So on the other hand, so this is one and other thing you can see. Okay. On the other hand, if x is in A is a self-adjoint operator. I mean, you can see that if you have a each singleton element here, you take the indicator function of the singleton. Any indicator function will give you a projection here. Okay. You can see that this I is nothing but summation lambda I 1 lambda I. Okay. Where lambda I is in omega. Summation lambda, I mean, summation over lambda in omega. This is what this is the identity. Okay. And these, each one of this is projection. Okay. From that. So here I will not spend much time. It's easy. If you have a x in here, then you have all those yeah. Now we want to get a homomorphism. Okay, we want to get a, so you want to define phi of f. Okay, that you so, and x is equal to x. I will just write it. It will be easy to, x is equal to lambda I 1. I mean pi. Okay. You need to go. So now you take omega equal to lambda 1 up to lambda n. This is my set. Okay. In this set, I want to define a function. If you have any function, I have to define. So then phi of f is equal to summation f of lambda I 1 the pi. That's all. This will, you can see this is a homomorphism. You can verify. So this gives the right homomorphism. So this is of self-adjoint operators and star homomorphism between this commutative algebra are related. Okay. We have, so I haven't erased it. So we have defined a measurement to be from a map from say A star to B star. So if you have here, if you have a random variable x, then you want to get a distribution on that. I mean, if you have a, if you have, so you, I mean, so if you have a phi from C of omega to A, okay, then phi star we get from A star to C of omega. This is one way of measurement. I mean, there we defined a different measurement. That is, we want to see whether the rho is altered or something. But this measurement we can do. That is, we have a rho here. I mean, C of star. Then we get a mu here. Okay. If you have a rho here, we have, you know, the prescription how to do. If you have a state here, that state will give you a probability distribution on omega. Okay. So that is how you get a, that's what measurement is. Okay. But we want to define what is called a joint measurement for two random variables. Okay. So this is the theorem. This is the uncertainty theorem. We want to prove that this is not possible. Okay. So suppose x, y are two elements in A. Okay. Maybe I will define it. Definition of joint measurement. Okay. Definition. So x, y are two in A self-adjoint. Okay. Okay. And sigma of x, sigma of y contained in R, the spectrum. Okay. Okay. A joint measurement of x and y, of xy, is a probability distribution on, I mean, this is just the star of C of omega 1, C of, I mean, you call this, okay, this call it as omega 1, omega 2. This is our usual notation. Okay. On omega 1 cross omega 2, such that you get that, and such that f of such that y of xy, this is the distribution, right? F of x summation over x and y. Okay. This is equal to rho of f of x. I will write it in the right terms, I mean, as maps, but this is what is satisfied. Okay. F of x is an operator. X is a self-adjoint operator, then you can define f of x, right? X is summation lambda I pi, then f of x is summation f of lambda I pi for any f. Okay, f defined on this. So, and the summation xy, y of xy, g of y equal to rho of g of y. Okay. This is what is called a joint measurement. Yes. So let's write it in terms of that, what we have. So this is equivalent to saying we have a map. I mean, what I am saying is, if you want, if measuring a single random variable means you have a random variable, single random, you fix the random variable x. Okay. So you fix the c of omega. That random variable corresponds to some c of omega, where omega is the spectrum of that. Okay. So you measuring a single random variable means you have a map from any the state space A star to C of omega. I mean the state space of C of omega. It gives a problem for each row, it gives a probability distribution on that. Here joint measurement means you have two random variables x and y. So you take the product space omega 1 cross omega 2, or C of omega 1 tells or C of omega 2 if you want, and you have a state on that. You have a product measure on that. You have a measure on that such that it evaluates this. Okay. So this is equivalent to saying you have a m from m star, okay, m star from A star to C of omega 1 tensor C of omega 2, right? Right now from A star only, such that m star of rho is the other way. M star of rho is there. M star of rho acting on any f tensor 1. I mean, m star of rho is a state here, so it acts on f tensor 1, right? M tensor rho is a state here, so it should act on f tensor 1, is rho of f of x. And m star of rho of 1 tensor g is rho of g of y. Okay? For all f in c of x, c of omega 1, g is c of omega. Okay? Yeah. This is what joint measurement means. So write it in the covariant version. Covariant version, we have a map from m from c of omega 1 tensor c of omega 2, okay, to a such that m of f tensor 1, okay, equal to f of x, right? That is true for all rho. Correct? M of 1 tensor g equal to g of y. Right? This is what it means. That is true for all rho. This is true for all rho. Okay? Then this is what it means. If you take the star of that row of m of 1 tensor G, this is what it means. So we want to say this is not possible. This is what we want to prove. Okay. Okay. This is the theorem. M from C of omega 1 to no from A, no. Is it right? Right? No, that is clear, no? Okay, what is that? There is nothing to prove. No, that's not what I want. I have row m star row. I have m star row acting on F. This is right. M star row acting on M tensor 1. This M star row is that pi. Okay, I have said there is a pi. That pi is nothing but M star row. Okay. When you have row acting on some F is just the expectation of that. Okay. So that is what the summation all that means. Expectation with respect to that. So M star row acting on F tensor 1 is row of F of x. That's what that says. Similarly, this. So if you take the contravariant, this is just covariant version of that. This is this row of M star of F tensor 1, M of F tensor 1, which is right, which is equal to row of F. So this statement is correct. Yeah. Okay. Okay. M of F tensor 1 equal to F of x. M of 1 tensor G equal to G of y. Then x and y commute. That means if it has a joint measurement, means this. If joint measurement is there, then it commutes. That's what this is. Proof is trivial. Okay. So first we want to say x and y commute. Okay. Okay. So this is true for anything. So we want to verify that condition of the multiplication theorem, which says the following: m of 1 tensor. I mean, what is x? If ix is from omega 1 to r, which is the identity function corresponding to this. I mean, and iy from omega 2 to r. Okay, identity function. Okay, identity functions. Okay. Then m of ix tensor 1. Okay. If you want ix, ix, I mean, star is same as this. Okay. Ix tensor 1, which is equal to x square. M of f tensor 1, f is ix. I mean, ix of x is x. Okay. Okay. The same as x. Okay. F of x is the whatever that homomorphism takes that f of, I mean, f of x is you know f of x. Okay. It's clear. Okay. So ix goes to x. So ix times this goes to x square. But then this is also same as m of ix. I mean, ix tensor 1 times m of ix tensor 1. Okay. So it satisfies that. Similarly, this is true for the same for y also. So I mean, now it's clear, right? I mean, the xy equal to m of ix tensor 1 into m of 1 tensor iy But because it satisfies the multiplication theorem thing, you can take it inside. M of Ex tensor 1 times Ix tensor 1, which is Ix tensor Iy. Okay? And you can change it if you want. M of Iy tensor 1, sorry, 1 tensor Iy into Ix. The same idea, we have done it several times. Okay? Times 1, okay? Which is same as M of 1 tensor Iy, okay? M of Ix tensor 1, which is, of course, y x. So they come, that's all. Xy equal to M of Ix tensor 1. No, sorry, M of Ix, no, M of, once again. Yeah, M of Ix tensor 1, M of I 1. No, that's a different theorem. No, we proved for something else. That is, we didn't prove for this. This is only, here we are not assuming. See, there you have the function coming from A star to A star tensor B. Okay? You have a, you get here, it's not like that. Here A star to B only. Where what is B is the question. B is determined by one random variable or two random. If it is determined by one random variable, it's a commutative thing we can do. If we have a two random variable, then B becomes C of omega 1 tensor C of omega 2. It's not possible. That's what this. There it is different. There you make a measurement, okay, make a reasonable measurement, whatever the reasonable measurement is, then the rho will be altered. That's what that says. That has nothing to do with this. That's a different uncertainty principle. This is for two random variables. Uncertainty for two they don't commute. If x and y don't commute, there is no joint measurement for them. That's what this says. Okay? I will prove one more version of thing, but I will prove it tomorrow. Point of the? No, this calculation says that we have to verify this. Now, if you have a random variable, we have to verify phi of A star A equal to phi of A star P of A. Then we can use the multiplication theorem. No? So I am just verifying this. There is star is same as this. Okay, that's what I have verified. Okay, so that I have verified. Once I have verified, I can do multiply with any B. That's what multiplication theorem. I mean, this is just trivial. Once you have multiplication theorem, this is just trivial. Okay? That's what I did. Okay? So that is a different version of uncertainty, which says that if you do a measurement, that means the rho will be changed. If it is not changed, then there is no real information. You get a scalar. Okay, there is no real. You don't get a actual reasonable information. That's what we say. Here, the next one we says that we have a general measurement. If you have one single random variable, we can always measure it. Okay, then we have a map. We know how to do that. Suppose if you have two random variables, you have a joint measurement. Each one can be measured. But once you measure the first one, the rho will be altered. That's what this says. The original theorem says rho will be altered. So you can't have the same measurement for the another one. Okay. In case you have joint measurement, that's what this statement says. Then they have to commute. Otherwise, there is no joint measurement. That's what this says. That's all. I will use there is a real inequality, Heisenberg inequality, that I will prove in the next class.